Swayam Prabha. Digital India. Educated India.
There's a few places here where I'm going to touch on what we refer to as the direct analysis method in the U.S. I wanted to do a relatively light touch on that. To understand some of how we approach stability bracing design, which is we're going to talk about some later in the week. It's important to understand what's going on with direct analysis method, or it's useful to understand. And you could say if there is a preferred method, well, the direct analysis method in the AISC specification is, you could say it's given preference because the main standard talks only about direct analysis method, and then you have to go to an appendix if you want to say, well, what's the requirements for effective length method? So I want to explain it just in a few words, whereas at Georgia Tech, I'll spend a couple of lectures with these few words. Direct analysis method is very related to approaches in the Eurocode. How can we do a design where we don't have to rely on getting buckling loads of the members? Or often it's said, can we do it without relying on effective length? Okay, and what it amounts to is either if we're doing direct analysis method or if we're using some of the methods in Eurocode, we're really just trying to say, how can we get a credible rough estimate of what are the real forces in the structure? Now, if we talk about the way we've just analyzed a few frames, we did not include geometric imperfections when we did that structural analysis. It was an analysis of the perfect geometry of the frame. And and we didn't include, if you're taking the structure up to strength, you typically we're designing members so on the member design rules, we're starting to get some inelasticity. We're not taking any reduction in the elastic stiffness. We're just analyzing using the nominal elastic stiffness. Okay. In Eurocode, as many of you may be better in tune with than me, there are approximations with notional lateral loads and we're going to talk a little bit about notional lateral loads here, that are an exaggeration of what would be needed to essentially match with actual initial side sway imperfections, and exaggerated to try to cover the bases and say, okay, well, actually we've got some inelasticity or whatever, and we need to get what's an estimate of the forces at strength conditions. In the U.S., could be argued right or wrong. The way things went is we felt that we should take a nominal stiffness reduction, just a very gross stiffness reduction of 0.8 on all elastic stiffness contributions. And then if we have any members in the structural system that have very heavy axial load, we have an additional what's referred to as an inelastic stiffness reduction factor that's put on the EI, the rigidity of those members. And so that's kind of a direct attempt to say, oh, we're going to get some reduction in stiffness as we're approaching strength. And we also have notional lateral load or direct modeling of the side sway imperfections that the notional lateral loads are equivalent to. And so a direct analysis, you can say, is really just, I call it a poor person's test simulation. So as a researcher, I can set up a structural analysis where I follow spread of plasticity through the structure. I put in initial residual stresses in the members. I say, oh, this is my imperfection that I'm starting with, geometrical imperfection. And I analyze and I say, oh, I've got something that I hope is going to be very close to actually what I would measure if I instrumented that structure in the lab and loaded it up. And the direct analysis method is basically trying to do that, but do it in a way that is practical for routine design. Eurocode, different perspective. They're attempting to do very similar things with managing the notional lateral loads, no stiffness reduction. Okay. All right. So with that said, I'd like to say a few things. I think first in this session, I want to talk a little bit about nominal out of plumbness and then the equivalent notional lateral loads. And I've got an exercise here that we can work through. We'll try my hand at the Wacom tablet for a bit at the end of topic 1. And so maybe not so grueling. We'll get a little bit break to work on some things a little bit hands-on there. And then I want to show you an example that I'm going to do it by direct analysis method of a single-story multi-bay frame. It's called in metal building industry a modular frame, where we'll look at the solution, and there I have actual plastic zone, basically test simulation analyses that we can compare to and see how that works. We'll also look at what we get from effective length method, so we can talk a little bit about, okay, where's the effective length method falling short? Why do we have these alternative methods that are becoming more and more in vogue? And that's kind of topic 3 that we'll do the wrap up there, comparing everything. All right, so learning objectives here. Okay, let's make sure everybody's in a good place with how can we apply notional lateral loads that are equivalent to certain nominal out of plumbness effects in building structures. We'll look at applying the direct analysis method to a representative, I'll call it a stability critical building frame. And then we'll wrap up with evaluating and comparing responses from the direct analysis method, the effective length method, versus what we would get from test simulation. Now, my best understanding of the Indian standard is your Indian standard is, I believe, is very close to AIC's effective length method when it comes to handling everything. You're getting a buckling result, or K-factors that feed into calculating a buckling result, and then you get buckling loads that feeds into your member strength formulas for axial, for bending. But you're analyzing the nominal elastic structure, perfect geometry, but for gravity-only load combinations, you use a 0.005 notional lateral load for the load coming in at each level. This is what I see. Direct analysis method, we're going to use 0.002. And so the next slide is going to talk about that a bit. So AISC has what they call the Code of Standard Practice, and that's basically prescriptions for building structural steel frames. Whereas let's say if I'm an erector or a contractor, I've built a steel frame, and this frame is the geometry is off, then the owner can say, well, here's the Code of Standard Practices. It says you have to be within this tolerance. So we're going to court, and you're going to have to fix this, right? So the maximum tolerance on the story drift in the Code of Standard Practice is basically story height over 500. So that's what we use as our basis. So 1 over 500 is 0.002. So we use that, whereas your base with a gravity-only load combination in the Indian standard is 0.005. And Eurocode would typically have a larger notional lateral load as well to try to say, okay, well, let's try to, through a larger load there, pick up on some of those other effects where we're losing stiffness and so forth. And so how do we apply this? Well, what I always have told engineers that if I've got software that will actually put in the imperfections for me, I'm going to use that. Now, Consteel is very sophisticated in terms of implementing a whole lot of stuff from Eurocode where it will basically put the imperfections in for you. And we'll explore just a few things with that, with stability bracing and a few other things where we'll actually put an imperfection into the analysis model to run it. So I like to do that. I think it's clearer. That's what you're analyzing. If you're using notional lateral loads, you're using something that's equivalent to that, and it can be a little bit difficult in some frame configurations to kind of understand what those notional lateral loads are. If you've got say a gable portal frame with a lean-to or with a mezzanine on the inside of it and so forth, and so you got a lot of some geometries are not perfectly rectangular. You start scratching your head about, well, what are my notional lateral loads here? You can figure it out and do it, but it's kind of it's more direct to use your smarts to just say, oh, let me just lean the frame over. Now I've accomplished what I need for these effects by explicitly modeling that. Now, for ordinary rectangular frames, it's not that hard to use notional load, and many software providers prefer it. You might say, why? Well, why? What I'm told is that one reason is, well, they've implemented those rules from various international standards for many years. Then it finally came to the US, so they're ready. The other thing is if they're handling it by loads, well, let me say it the other way. If they were handling it by explicitly changing the geometry, they've got to reformulate, rebuild the stiffness matrix for every geometrical configuration that they want to solve. Whereas if they do it in loads, I've got one analysis where I've built the stiffness equations for the structure, I'm done. Oh, I can put these different notional lateral loads on there so it's a bit faster for them. All right, so we call it a 0.02 y sub I, where y sub I is the vertical load at a given level. So how does that work? And I'm not going to go there with the alpha y sub I. There's some things that get confusing because of ASD and the alpha and how that's applied here, but that's not so relevant here. So here's two stories out of a frame to try to illustrate. Where does that 0.002 y sub I come from? Now, if we look at the story on the top here, what we're saying is it's a P large delta effect. So we're looking at we want to get P large delta shears associated with the initial out of plumbness. So the delta naught, I plus 1 of this story, I've got a summation P, the vertical load that's carried by this story, and if I multiply my delta naught I plus 1 divided by the story height for story I plus 1, I've got a story P delta shear that gives the same effect as the vertical load acting through that initial out of plumbness. Okay? That's a P delta shear though, it's not a notional load. Now I can do the same on the lower story here, the story I. Same equations but with subscript I. All right, well, Newton's third law, I should have equal and opposite forces from each of these stories coming into the free body diagram of the floor level here. And so when I add up those forces that come in at this floor level, the difference in the summation p's is y sub I. And I can see that I'm ending up with opposite p delta shears here that amount to, when I sum those, I factor out the 0.002, I see that some pi minus some pi plus 1, that's really just the vertical load that's applied at this story. That's my y, capital Y sub I. So that's the way AISC writes this. So you might say, okay, good. I'm ready to do notional loads now. Here's a big floor plan, and it's a flexible diaphragm. What do we do with the notional loads? If you're worried about a flexible diaphragm, you would basically say, well, everywhere that I have vertical load coming into the columns, I've got a notional load that's associated with that column. So I do each column by column by column. If it's a relatively rigid floor, and I don't have anything special like a big vault in one corner of the building or whatever that's very heavy, if it's fairly well distributed, I'll just do one Y sub I for the whole frame and then look at its effects. That's what this slide is illustrating. All right, we're still not done. How do we apply these loads? Well, what the AISC gives as guidance is, well, you need to apply them in a direction for greatest destabilizing effect. And so we're going to use a few slides to kind of illustrate this. And then, well, what pattern? If it's a tall building, I'll define tall as more than seven or 10 stories. So we don't build too many of those. In those, it may make sense that we don't want to do this just uniform up the entire structure. If it's a very tall structure, that's an awful big lean after a while. And in a tall building, they're going to have better tolerance than that on the overall verticality of the frame over the entire height of the building. So that kind of gets a special situation. But for most routine things, less than 7 to 10 stories, we just put a uniform lean on the entire building. Okay. All right, so how do we apply it? If it's a gravity-only load combination, we're basically told we need to apply either the imperfection or the notional load independently in the two orthogonal orientations that approximate the principal stiffness directions of the structure. So independently means one at a time. I believe I see some language that relates to this in the Indian standard. We don't have to do any off-axis notional loads. We don't need a diagonal notional loading on a three-dimensional building frame. We just look at applying these in the principal directions. Let's try to keep things simple. We don't need any torsional notional load that would correspond to, what might I do with twist? I know of one structure that was in Moscow that a company, Halverson and Associates, it's a very reputable designer in the U.S., was basically doing the Moscow Tower. And this building, the footprint of for the building was basically a cruciform or a plus sign. And if you look back at your structural mechanics, a cruciform is absolutely the weakest thing you could possibly do in torsion. And so in that case, Halverson and Associates actually did some things where they were looking at notional loadings and torsion on the building because they wanted to make sure they stayed out of trouble with that. But most of the time, unless you got something special like that, we don't want to bother with it. In the American codes, once we go to the load standard, there'll be various aspects with wind loading. That's basically eccentricities in the wind loading. And also we could look at seismic loading. There's seismic eccentricities that we handle in the design rules. So there's plenty there to handle things that would relate to torsion without having to muck it up further with the notional load requirements. So for gravity load only combinations, again, plus or minus directions along what we've just mentioned. So we have a total of 4 gravity load combinations now. So I need to run an analysis for my factored gravity load with dead load. Oh my goodness, I've got to do 4 now instead of 1, and engineers complain about that. If it's a fairly simple case, basically structures that don't exhibit any side sway under gravity load, and if you are enforcing symmetry in your design by your grouping of elements in your design, then you can basically simplify it to needing to apply only 2. And also for simple cases where the structure's side sway deformations are in the same direction in all the levels, you can apply basically your notional load or your imperfection in the direction that would tend to increase the side sway. That's going to be the biggest destabilizing effect. That's what this bullet says. And you absolutely do not have to start playing the game of saying, oh, I've got the structure's kind of swaying to the right, but if I put a notional load to the left with that, in this one little column over here, I get a little bit larger moment. No, you don't have to do that. It's the overall effects. So lots to it. I think there's a lot of these things that are implicitly intended in the Indian standard, but I think the Indian standard is relatively terse, basically saying, I do see something there about needing to, you don't apply them simultaneously in orthogonal directions. Those are separate and so forth. A lot of this other things I just laid out for you, it's like, oh gosh, I guess I do have to think about that, huh? Now for lateral load combinations, in your standard, you don't apply notional load at all. In AISC, for most frames, we don't. But if it's a structure where the amplification, the side sway amplification is relatively large, basically if B2 is larger than 1.5, then the AISC standard basically says that frame is going to be tricky. You better put the notional load on with the lateral load. And you put it on in the direction that would, of course, increase the lateral loading effects. But you don't have to do torsional notional lateral load ever. Your wind, your seismic eccentricities will give you plenty of torsional effects. And there's often confusion about P delta shears at the foundation level. So if we kind of look at what we've got here, we had this graphic up earlier. And so at the floor level there that we focused on, clearly the notional load is 0.002 y sub I in AISC. For the Indian standard, it would be 0.005 y sub I. But I've received the question before, okay, I ran my analysis by the AISC, it's a gravity load, but not only gravity loading on the frame, but now because of these notional loads, I've got a story shear at my foundation. How could that be? This is only gravity load. Well, it's that way because at the foundation, you left out the P delta shear that went into determining the notional loads. So you'll always want to include that P delta shear at the foundation level if you're carrying your results to your foundation and then designing that. And so first of all, what we may want to do, and this is different than my iPad tablet, so we'll see how good I am at it. I want to draw a diagram of the axial forces in the column. Okay? So we often call this, in folks I work with, they may call it this a gravity load takedown, right, on the structure. So clearly, what is the axial force in the top level here? What's the axial compression? Checking if you're still awake this late in the day. You would say that axial force is what, 1,000? Okay. And then if we go to the next level down, we have another 100 kips or kilonewtons coming in here. And so if I'm doing a column axial load diagram, I'm getting then 1,100 here, right? And then the next level down, I've got 1,200. Correct? All right. So now, let's suppose that, now if with notional lateral loading, we usually say we're going to put a uniform lean up the entire frame. But suppose for purposes of discussion, we're saying, I have an out of plumbness just in that middle level, okay? So then, physically, if we consider drawing moments in this structure, so these loads, okay, all right, there we go, good. I like this. Do I have any moment in the, now this, again, back to a cantilever, but this is kind of representative of everything in a given story, right? So do I have any moments in the top story? Yes, no? It's just a concentric load of 1,000, and so that's all zero there, okay? But now, when I get to the next level, I have a 1 in 500 out of plumbness on that. So I start at 0, but I end up with a value that would be, if let's see if I can move that down. So for a 120 inch height there, I would have 0.24 inches out of plumb between the top and the bottom. So what should my moment be at the bottom? I want you to tell me this. You're being very silent. Can you calculate the moment that I should have at the bottom of that middle story? Okay, 264. Okay, good. So we've got basically the 1,100 acting through the 0.24, right? So 260, 1,100. Okay, good. You're right on it. And then in the bottom level, constant moment at 264, right? All right. So physically, that's what's going on. It's just gravity loads, and I've got an out of plumbness in that middle level, right? So I would end up producing, because of that imperfection, if you will. Keep my knee away from that box. That we're producing these internal moments. This is a first order analysis calculation. Now if I run an analysis, I'm going to get additional moments because these moments cause bending, so it's going to sway, and I'll get some additional moments on top of that. But that's not what we're dealing with when we're doing with the notional lateral load. Notional lateral load is just picking up on the effects of those initial out of plumbness values. So, what are the equivalent lateral loads I should put on this frame if I just wanted to analyze the frame without actually modeling that out of plumbness? And the hint there, you could, let's call them P delta shears instead of notional loads here. Do I have any P delta shear in the top story? No, there's no out of plumbness. None in the bottom story. So it's just the middle story. I need a P delta shear. And so if I apply equal and opposite shears, those are P delta shears to that story. And if I do, P times delta over L, well, that's equal to, what's the P here? The P we're looking at producing the moment there at the bottom of that story is 1,100, right? It's the P in that story. So 1,100. Oops, trying my luck at using the eraser. Good. Well, come on. All right, now the professor needs to figure out how to get it to go back to the pen. Let's see. Pen, oh, right there. Okay. 1100. 1100 times, all right, that's a bad 1100, but oh my goodness. Come on. Give me a second. All right, 1100. Then that times a delta, 0.24 over L. That's a story height, 120 here. All right, so my P delta shear is 2.2, equal and opposite. That's a P delta shear. It's not a notional load. But if I had uniform lean on the structure, I would do that for each story in the frame, and we would end up with our notional loads that are the 0.002 y sub I if it's 1 in 500 at each of the stories. Now, here's a little hypothetical with another frame, so kind of something to try to represent a frame with 4 stories, 2 bays, and suppose that we've got bracing in the 2 bays on the right in the bottom 2 stories of the frame. Now we know that whenever we have walls or lateral bracing, that's much stiffer than what we'd have with a moment frame. So let's kind of go to the extreme with that just for illustration purposes. Let's suppose that bracing system is so stiff in those bottom 2 stories, any lateral load effects get taken entirely by that brace bay. Okay, so that's the frame. So now I'd like us to do a few things with it. So if we go to the next page, I want to do a gravity load takedown on the structure for all the columns. So kind of speed this along here. So this would be 100. This column would have 200. This column would have 300, given the loads I showed you. This column would have 400. And same thing, I'll do a little ditto marks. Well, I'll just say it. The same thing for the other 2 column lines. Same forces all the way from top to bottom down the frame. Okay. All right. So that's basically the column gravity load takedowns. So now, given those loads, if we have a uniform lean on the structure, what are the P delta shears that are coming in? And so at the top level, I've got my column loads of 100. So I'd have my HP delta is equal to, that's my P delta naught over L, equal to 100 times basically 0.002 is my delta naught over L. So it's equal to 0.2. And so I would have in each of my columns P delta shears, so all these are 0.2. Okay. It's like all the columns here. This is 100. This is 200. This is 300. This is 400. I'm just not labeling all the columns. All right, I'll change colors here to emphasize, if I can figure that out. Color. Okay, how about blue? See if that works. Okay, so if I look at the next story down, that story has, oh, come on, what did I do? Oh, I think I turned on a recording rather than, okay, all right. Oh, that's not the right one. Let's see if I got it. No, okay, all right. Always helps to work a system and practice it before you use it. Okay, that's my pen. So how do I get my colors? That's not color. Which one? No, well, it doesn't like it. Okay. Oh, okay, I think I've got color now. All right, let's see. All right, so, yay, I got blue. All right, so we're going to have Next story down, we basically, same thing, HP delta, but the P is now 200, right? So what's my P delta shear in each of my columns? This is going to be 0.4, correct? All right, so now if I change to orange, well let me finish filling that one out. That's 0.4. So if I go to the next one, this is, so I've got 300 in that column times 0.002, that's 0.6. So those are the P delta shears in the columns at that level. Oops. And then lastly, how about fuchsia? So same calculation, 0.8 would be the P delta shears, so 0.8, right? Okay, so how are the AISC notional lateral loads, which are 0.002 y sub I, related to these P delta shears? Well, we just take what's coming into the floor levels that we just analyzed from the P delta shears, and we're going to add them up wherever we have vertical load basically being transferred to the columns. We get a notional lateral load. And so what we can see that we get from this is notional lateral load at the top is clearly 0.2 on all the columns. But now we go down, we've got 0.4 minus 0.2. Oh, it's 0.2 again. So what we can see is on this particular frame in our example, we basically have 100 applied at the top of the columns coming in at each level. And once we do the P delta shears, then sum up everything at the joints, we're getting 0.2 throughout. Everybody in a good place? All right, so now the question is, well, if I've got all these notional lateral loads on the frame, what would be my reactions at the base of the structure? So I have a graphic on the next page to illustrate this, but it may be easiest to understand if we do it here on this graphic. I'll change to purple. So again, if we go back to what I suggested as just a little hypothetical for purposes of illustrating things before, let's suppose that those brace bents are infinitely stiff compared to the moment frame column on the far left. And so all the story shear is going to go to those. But we'll assume from symmetry of those bays, we basically get, if we sum everything up, we've got 0.8 lateral load at each of the columns, summing all the 0.2s, times 3 columns, or 2.4. And then half of it goes to each base here, so I'd have 1.2 and 1.2, roughly. All right? So now the foundation engineer says, why are you giving me a lateral load? This is vertical. This is a frame that has only vertical load on it. Oh, because the standard didn't say put in the P delta shear force at the base. That, in other words, up here, let's see, I think that's a highlighter. We left those out when we went to part C. So let's consider the reactions from those. And again, I have a graphic on the next slide to try to show that, but I think it might make sense to just try to show it here. So I'll try to show it in orange. And so if I applied that P delta shear at the foundation, well, it's at the foundation. If it's a rigid foundation, it just goes into the support, right? So the foundation reactions for the directions of those P delta shears to the left at the foundation level, the foundation reactions, I'll put it a little bit lower here, are 0.8, 0.8, and 0.8. So what this is trying to illustrate is, I think we can close out by saying this. So if we sum these two effects, we'll basically get, well, 0.8 is what we've got here. So this would be a 0.4 to the left, and this would be a 0.4 to the left. Okay? And so the last question is, what do we expect the reactions to be at the foundation? Well, the sum of the reactions has to be 0. There's no physical lateral load on this frame. But because of different relative stiffnesses in the system, you can get self-equilibrating forces that relate to your notional lateral loads at the foundation level that are also physical, because you would see those showing up also from the physical vertical lack of verticality. And so this example here, total reaction at the base is 0, 0.8 minus 0.4 minus 0.4, but we've got non-zero values at some of the columns. And the mantra with this is, okay, from the notional lateral loads, you got only the 1.2s there that are in blue at the base. You say, okay, wait a minute, I should have 0 load on the foundation. Okay, we'll put in the P delta shears at the foundation. Those are the 0.8s. And then sum everything, you've got what should be going into your foundation. Does that make sense? Any questions there? Usually, I think folks find that kind of helpful in terms of improving understanding of what we're doing with notional lateral load. All right, so let's wrap up with the most intense part of the lecture. We'll save the best for last. Let me figure out how to stop screen share here.